In section 4.4, we're going to talk about inference for sampling, which is where we're attempting to use the results of our sample and apply them to a broader population. In the past two sections, we talked a lot about how to sample poorly, voluntary response samples, convenience samples, along with all the biases that they can suffer from, non-response, response bias, undercoverage, etc. And we also talked about how we want to include randomization in any valid sample. More specifically, we want to conduct what's called a simple random sample. And in a simple random sample, each individual has the same chance to be chosen, and each sample of size n has the same chance to be chosen. When it comes to conducting a simple random sample, there's three primary ways that we'll go about doing it. The first is to take all our subjects' names, put them in a hat, mix those names up, and then draw random selections to identify the people that we're going to sample. The next option is to number them in a list. And we're going to number them from 1 to n. N is just however many there are. And then we're going to use a random number generator that's just going to give us random numbers. So if we have 100 subjects, we number them from 1 to 100, and then we ask our random number generator, give us a number from 1 to 100. It picks 73. We survey that person. Okay? When we do this, we want to make sure we ignore any repeat selections, at least in most cases. All right, and then option 3, we're going to start off that same way, number them from 1 to n again, but this time instead of using a random number generator, we're going to use a random number table, which is just a string of random numbers. Anything that's outside of that range, if it's 1 to 100, and we end up with 207, that's outside the range, we just ignore it. All right. In the end, we'll sample those subjects corresponding to the numbers that the table produced. Now that last option, the one with a number table, is the trickiest to understand, so we'll start with an example for that one. Down here, you can see we have table D showing random digits of numbers. Let's say we want to randomly select 50 subjects out of a population that has 500 subjects in it. To start, we're going to number the subjects in our population from 1 to 500. Okay, and really we're going to number from 001 to 500. And that's because when we look at the numbers in this table, we're looking at them 3 digits at a time. Why 3 digits? Because the size of our population is a 3-digit number. All right, if there were only 99 people in our population, we could just look at a 2-digit number. If there were 10,000, we would look at 5-digit numbers. All right, so when I say we're looking at a 3-digit number, we're just going to look at the first 3 digits. 192 is the first person that we would select in our sample. Okay, we'd go to 192, we'd ask them that question, then we'd go to 239 as the next one. And then 503, this one we're going to throw out because it's not in the range, it's outside of 500. And then we just keep going through, okay, throw out any that are outside 001 to 500, and we would throw out any numbers that happen to repeat. Throwing out any of those repeat numbers is important because when we're choosing a simple random sample, we're doing it without replacement, meaning that once we pick someone, they can't be selected again. It's important that if we're drawing our sample from a random number table or a random number generator, we need to throw out any repeated numbers. We'll use this example to go over the other 2 types of methods. When landfills run out of room, they are sometimes converted into parks. Does the presence of a landfill underneath affect the trees that grow in the park? One such park has 283 trees, and the researchers want to closely inspect a sample of 20 trees. So to start, for part A, we're going to describe how to select a simple random sample. We can just write SRS for simple random sample of 20 trees using slips of paper. Now, when using slips of paper, normally we write the names of the subjects on paper and put it into a hat. However, this is a little different because we're dealing with trees. So we'd want to start by numbering the trees and then writing those numbers on slips of paper. Put all those slips of paper into a hat, mix them up, and randomly select 20 of them. Those are the trees that we'll inspect. Now let's say we want to use a random number generator instead of using those slips of paper. This is the most common way that we conduct a simple random sample. So we'll start by labeling our subjects in the same way we did before, just giving all those trees numbers. There's nothing random about it at this point. We can just number them in the order that we see them. Then we're going to randomly select our sample by using a random number generator and asking us to give it random numbers between 1 and 283, and we want to ignore any repeated numbers that we get. And those numbers that we get are going to correspond to the 20 trees that we're going to more closely inspect. Our response variable in this case is going to be the diameter of the trees. So once we selected our 20 trees, we're going to go and measure the diameter of all 20 of them, and we're going to average those diameter to get our statistic. Remember, a statistic is based on a sample, in this case the sample of 20 trees, and the parameter would be the average diameter of all 283 trees in this park. Now, regardless of which method we used, whether it was the slips of paper or a number table or a number generator, every sample of 20 trees that we take is going to give a different statistic, meaning that if you did this and I did this, we would get a different average diameter of 20 trees. Statistics vary, parameters don't vary. There's some true average diameter of all of these trees, but when we just take 20 of them, it's going to jump around a bit. And this is called sampling variability. So the fact that different random samples of the same size will change as we take those samples is sampling variability. If you look at the text at all, you'll see that a recurring example in this chapter is randomly selecting words from the Federalist Papers. In this example, we're randomly selecting 5 words. We average their word lengths, and then we do this 50 different times. So when we look at this dot plot on the bottom here, the dots are not representing word lengths, but actually the average word lengths of 5 randomly selected words. This dot here, this red one, means that we chose 5 words that had an average word length of 4. They range from 2.2 to 8.0. Okay, so we can see sampling variability at play in this example here. We have a pretty wide range of averages. When we take a sample, right, it's going to vary around the true average. You can see that this is starting to pile up right around this spot right here, and that's probably about where the actual average is. Now, this is going to happen all the time when we take a sample. So when we get a sample, we don't expect it to match the population average exactly. We're just hoping that it gets close to it. And the way we can get closer and closer is by taking a larger sample size. So on the right here, instead of taking a sample of size 5, we take a sample of size 20, and we can see that this is a lot less spread out. Now we're only going from 4 to about 6.2, where originally we were going from 2.2 to 8.0. Now both of these, if we look at them and kind of imagine if we were to keep doing this, keep taking 5 words and averaging them over here, or 20 words and averaging them over here, we can see that they're going to start to pile up right around the center here. And in both of these, the center is right around like 4.9 or 5. So increasing the sample size reduces that variability. It's going to get us estimates that are more consistently close to that true average of around 5. Now, what it doesn't do is reduce the bias. So if there was any kind of response bias or voluntary response bias or anything like that, when we collected our data, none of that goes away just by taking a larger sample. Now, the whole point of taking a sample is to give us some idea about a larger population. In most cases, conducting a census is unreasonable, whether it's too expensive or too time-consuming or just impossible to do. So instead of conduct a census where we talk to everybody, we take a sample, and we're hoping that that sample is representative of the population. Right? When we draw conclusions based on that sample, that's called inference. We're inferring information about a population based on what we know about the sample.